Hello, mathematicians. We are wrapping up this entire unit. To recap, this unit is about creating models to represent situations. So, right now, we've looked a lot at what it means to be a quadratic equation, which is we're focusing on quadratic models in this unit, what it means to be key behaviors of quadratics, how to interpret when models are already given to us, right? When we're given an equation that represents that situation, how do we then interpret that? Plug in values, know what it means to be a y-intercept, know what it means to be an x-intercept. Our last part, which is arguably the hardest part, is that we're going to learn how to then create a quadratic model given a specific real world situation. We've already been creating models just from the pure algebra. So starting with 9.1, we just looked at how do we create it when we just have points. But a lot of us felt a little bit hesitant on that type of problem because it's hard. So now we're taking it a step up and we're trying to create that from information that we're given. Sometimes it's the same process of trying to find points in a problem that's given to us and creating a system of equations, but also sometimes it's a relationship that we're building off of that eventually turns into a quadratic equation. And remember from 9.1 at the very beginning, we had this little like, hey, this is what you're looking for to know that it's going to be a quadratic model. And one of the things is any problem involving area will be a quadratic model because you're taking one dimension, which is x, and another dimension, which would be, I know it's y, but we'll say for this case, and you'll see how this happens, also x. And if you're multiplying them together, x times x, you get x squared. So you're quadratics, right? So for your quadratic equations, area will always provide you with a variable squared, which is your quadratic. Also projectile motion, as you can see there, but that's not what this first problem is. This first problem is about area. So we have a rectangular mirror and it has a perimeter of 260 degrees. With all of these problems, if you don't originally have a picture, draw the picture, sketch it out. So, okay, a rectangular mirror and it has perimeter of 260. Well, if I wanted to talk about the perimeter, I would probably label my dimensions, right? I would probably say, because I want to say, oh, well, all of the sides add up to 260, so I need to have things that represent the sides. Well, that's x and y, and I can say, oh, well, then 2x plus 2y equals 260, right? Perimeter, just all the sides added up. I just did that to represent that. So I've represented right now visually and algebraically all of the information that I'm originally given. I haven't even read the rest of the problem, but I've got that down and ready to go to use for later. The length of the mirror is x. It doesn't matter which one's x or y. It says find the height of the mirror in terms of x. This phrase, in terms of x, means that we want to write an equation where your input is x. In other words, y, the height, which it isn't in my image, but you can imagine we would just turn it on its side and it would still work, where y is going to be related to x, but in terms of x means I want y by itself, right? Y equals 3x plus 5 is an equation for y in terms of x. F of t equals 24t minus 30 is an equation in terms of t. So that's all it means is that we want to have our input be x and we need to have the other variable isolated. Okay, well, I'm looking for a relationship. If I want to write an equation that involves these guys, I'm looking for a relationship that connects the two. I've been given that it's a rectangle and I've been given that it's a perimeter. And because I took that information from the very beginning to say, hey, that's that relationship together, I already have a relationship that involves y and x. So now, just to get it in terms of x, I need to isolate for y. I subtract 2x on both sides, which you could have done negative 2x plus 260, totally fine. And I'm going to divide everything by 2. Divide by 2, divide by 2, divide by 2. If that is something that you struggle with, isolating for a variable, then I'm going to write it down on my to-do list to make sure to add it to your additional resources. You will have by the end of today and isolate variable practice IXL on additional practice. So if isolating for variable is something like doing this process is something that stresses you out, there will be practice for that on your additional resources page. All right, so we just found out y in terms of x by using the relationship that was given to us in the beginning. We wouldn't have been able to do that if we didn't have the 260. So if you're asked to do that, you need to look at the information you've been given and see like, hey, was a relationship established at the beginning that I could turn into an equation to then isolate. It says then find an equation for the area of the mirror showing area A on the y-axis and length x on the x-axis. Choose a suitable domain. Okay. We want an equation where A is area and x is the length. If I were to talk about the area of this rectangle, I would say, okay, area equals, I cannot keep lead, area equals x times y. I have more than one variable. I've got an x and I have a y. I need A to be my output. Right now I have two different inputs, right? X and y are on this side as inputs. A has to be there as my output, which means I have too many inputs. How you move from too many inputs to only one input, we only want x to be our input. That means we don't want y anymore. We want it to go away. Well, notice we just wrote a relationship that involved y that could be written involving x. Y is interchangeable with 130 minus x. They're the same thing. Like a puzzle piece, y could go away and you could write in its place 130 minus x. So we take the idea of, well, hey, area is equal to x times y, and I substitute in this part for y. And now notice that I now have only one input, x. I could expand it by distributing, right, to both pieces. And you can see here, oh, that's a quadratic. So this is what I meant at the beginning where I was like, well, technically your area is x times y, but it's going to be kind of like x times x. It's because we have to, with these types of problems, eliminate one of the inputs. How we eliminate one of the inputs is we establish another relationship that can be substituted in for that input. And what happens is then you eliminate that input by replacing it with a relationship involving the other input. So you only have one input. Okay, that's our equation. We want to find a suitable domain and range. Best way to look at a suitable domain and range is to graph it. And because we are in the applications course, we need to make sure that we're also thinking about this. I just standardized the zoom, and then I'm going to zoom fit it. We also need to talk about the, I'm also going to zoom out because I know it's supposed to be a parabola and it doesn't look like one yet. We need to take into consideration the real world implications. Can you have negative area? Can you have negative side length? No. So we know at least we're in the positives. So that's part of our domain restriction. But also notice with parabolas, we will always have a range restriction where the range can only get to a certain point. Okay. So the range here, it's left over from previous work that I've done on my calculator. So I'm going to delete all those previous points. My range means I'm less than whatever the maximum value is. I can't get larger than that area, but I also can't go into the negatives. So I've got some restrictions in terms of the maximum. Domain, I also need to take into consideration that my area can never be negative. So I need to figure out where am I in between for the domain. I can start at 0 and I can go to here, whatever makes that area 0 over here. So that's going to be the domain that I'm living in. And then my range, I just can't go above here and I just can't go into the negative. So I need to find out what are those restrictions. Go ahead and try that on your own. I have faith that you can find out what those values are. But if you are lost, give it your best try and we'll talk about it. Okay, domain, curly brackets, x, such that I'm going to check out where my intercepts are. Remember that your x-intercepts are your zeros, and I have to do them one at a time. I'm pretty sure this is 0. I can also tell from this equation that it would be 0 because if I multiply anything by 0, the whole thing becomes 0. So it starts at 0. That makes sense. If I had a side length of 0, that my area would be 0. But just always good to double check. Have you ever done that before where you're like, I'm pretty sure I know the answer, but I'll use my calculator. And then you get the answer and you're like, that was silly. I could have just done that on my own. And then the other x-intercept is 130. Remember your different versions of the quadratic equations. This is fully factored form, so it gives you your x-intercepts right away, 0 and 130. So it could have been done without using your calculator, but that's fine. So we're going between 0 and 130. So x such that x lives between 0 and 130. Our range is, not y, a, right? A of x, such that a of x must live between, we know 0 is our minimum here, and now I need to figure out what is the maximum the area could be. So I go to my maximum, boom, boom, boom. My maximum occurs at a length of 65, and that's 4.23 e plus 3. Remember that that is scientific notation, meaning I move that decimal to the right 3 times, which means that's 4,230. Oops. And that would be your domain and your range. All right. Coordinates of the points where the graph intercepts the x-axis. Well, we already figured that out because we talked about domain. So those coordinates are involving these guys right here. You can do this on your own.